introduction, in this report, we focus on two widely used windowing function, which is the rectangular and Gaussian windows. These windows are selected for their unique characteristic and diverse application in digital signal processing. The rectangular window is known for its simplicity and high frequency resolution, that making it suitable for analyzing signal with well-defined continuous frequencies. On the other hand, the Gaussian window excels in minimizing spectral leakage, especially in time frequency analysis, and provides smooth transitions that are valuable in noise reduction and artifact minimization. The design principle, characteristic, and practical application of this window are explored in detail in this subsequent section.
Good day everyone. Now, I will be talking about the Gaussian window filter. Now, this filter can be defined as the mathematical expression given, where the capital N is the window length, the smaller n is the window index, and the sigma is the standard deviation of the window. Now, the key parameter of this filter is that the sigma controls the width of the Gaussian window. The smaller value of the sigma will make the window more rectangular, which larger values result in smoother transition and lower side lobe levels. Now, there are three frequency characteristics of this Gaussian window. The Gaussian window suppresses side lobes effectively, especially with the larger sigma value. This results in very low spectral leakage. Next, the main lobe is typically wider than other windows, like the Kaiser or Hamming windows, which results in lower frequency resolution. And lastly, the Gaussian window is known for its smooth bell-shaped curve that reduces the ringing effect, which makes it more suitable for time frequency analysis. There are many advantages of using Gaussian window, but I only talk two of it now. The Gaussian window's smooth shape allows it to provide excellent results when analyzing signals with both time and frequency components, such as chirp signals or audio signals. Next, the standard deviation parameter, the sigma, can be adjusted to control the window shape and frequency characteristics, giving it flexibility in design. Meanwhile, the disadvantages of this Gaussian window is that the Gaussian window's wider main lobe limits its frequency resolution, so it's not ideal for application where high resolution is critical.
Okay, now I will be explaining about the rectangular window filter. As you can see, in finite impulse response filter, rectangular window is widely used in window designing and analysis. It is because rectangular window filter are the most simplest form of window function. So since its simplicity, as you can see, the formula of the rectangular window can be defined as the formula given, which is 0. The window will be 1 from 0 to specific number to number of in time index until the capital N, which is the number of sample that we wanted to create. So next, the example. So as you can see, the example you can use here is the n equal to 50. So as we can see, the first graph, you can see that rectangular window implies the name itself. It has the rectangular shape in it. So the graph looks rectangular, implies the rectangular window filter. So the rectangular window filter will be apply the Fourier transform to get its frequency characteristic. From this frequency characteristic, we can see this the characteristic of the filter lah. And then for proper example, we'll be using a sample signal, which is in this example is sinusoidal signal. The sinusoidal signal will undergo Fourier transform to form each change into frequency domain. So the resulting to the second part of the graph, the red graph. So when we convolute the sinusoidal signal with the rectangular filter, it will form the resultant graph, the blue one. So the result of the convolution, as you can see, is it have much sharper main lobe, which making much more higher resolution. And if you can also see the side lobes have less fluctuation, means it have less noise disturbance. However, if we see in the middle part of the graph, there are fluctuation of energy, there are leakage of energy. So from that example, we can see there are a bit of advantages and disadvantages. First, the advantages is rectangular window is simple, and second, it is have a main lobe, narrow main lobe, so have good frequency resolution. And finally, it preserve the energy so that the signal doesn't lose energy even after the rectangular filter. For disadvantages of rectangular window filter, it have high spectral leakage. So that means there are the energy causing the adjacent frequencies to be fluctuating. So it causes problem to our signals. And then abrupt edges, since the high resolution, there are sharp edge of from low amplitude to high amplitude, causing discontinuities for our signal. Lastly, it limited control, since rectangular window is very simple. It lacks the ability to adjust and modify our signal into desired one. So we will get into our topic, and the next topic, which designing the filtering window. There are two filtering window that we will use to designing the window filter. One is a rectangular window, and next another is a Gaussian Gaussian filtering windowing. Okay, for the rectangular window, these are the steps in designing the rectangular window filter. So first step is define the filter specification. As we can see within the coding, the FC, which is the cutoff frequency, we set desired cutoff frequency. In this case, in this example, we use 100, and decide the between the previous formula, which is the length of the filter window. So in this case, we are using 21. Step number 2 is the sample the desired impulse response using the sync function. In this case, we are creating an FIR filter, low pass filter FIR. So that's the shown the coding. And then step 3, we will apply the rectangular window to the previous step 2. So we can call the rectangular window by the function h rectangular as the previous code. So that's the step 3. Okay. Next, the fourth step, evaluate the frequency response. So we will evaluate this by using the frequency function call, and we will refer to the our filtering window, which is the H rectangular. And finally, we'll be plotting the all of our data and rectangular window and its frequency characteristic. So this next is just to visualize. We can see that our rectangular filtering window. So you can see first we plot the result, plot the time domain impulse response, subplot, and then the next coding is, as you can see, the previous plot, and then the previous plot for the rectangular window, and then the next is the plotting for the frequency response. You can see the list goes on. Frequency response of rectangular window FIR filter, and from all of the coding, the result we have this figure. So we can see there is rectangular window filter, the rectangular shape, and then the below show the frequency response of the rectangular window, which is the characteristic. You can see the main lobe is big and the side lobe is much smaller. You can also see there are the sharp bump on the bottom side, which shows the abrupt signal of changes amplitude. So it should show the characteristic of the rectangular window.
For designing Gaussian windows, I made the example coding of Gaussian windows. This code generates and filters a noisy sine wave using a Gaussian window filter and visualize the result. It begins by defining the signal parameters that we set the sampling frequency of 500 Hz, a time vector spanning 1 second, and a sine wave at 5 Hz mixed with Gaussian noise to simulate a noise signal. A Gaussian window is then designed with a specific filter size of 55 and a standard deviation of 10, and creating a symmetric vector based on the Gaussian function. This window is normalized to ensure its value sum to 1 and preserving the signal's amplitude. The frequency response of the Gaussian filter is computed using the Friis function, which returns the magnitude response over 1024 frequency points for the given sampling rate. The noisy signal is then filtered by convolving it with the Gaussian window, with the same option ensuring the output signal matches the input signal length. The results are displayed in two subplots. The first compares the original noisy signal and the filter signal that in blue color, while the second shows the magnitude response of the Gaussian filter in the frequency domain. This process demonstrates how a Gaussian window filters smooth noise while retaining the signal's key characteristics.
Application of Gaussian window can be seen in the magnetic resonance imaging, known as MRI. Now, the Gaussian window are applied to filter MRI data to reduce high-frequency noise while preserving important image details, ensuring smoother transitions in the image. Next, in MRI, the Gaussian window is used during K-space data acquisition to reduce truncation artifacts, called the Gibbs ringing. By applying the Gaussian window in the K-space, the edges of the image are softened, leading to a more visually appealing and diagnostically useful image. Next, Gaussian windows help in localized signal analysis, such as in dynamic or functional MRI, where spatial and temporal resolution are critical. And lastly, during MRI reconstruction algorithms, like the Fourier transform, Gaussian windows ensure smooth interpolation and transition between the data points.
The digital analyzer for digital oscilloscope is example of real-world application for a rectangular window. First, spectrum analysis. Rectangular windows are used for analyzing signal in the frequency domain, such as during a fast Fourier transform. They preserve the original signal's energy, making them ideal for signal with well-defined, continuous frequencies, net simplicity, and speed. Rectangular windows are computationally efficient, making them suitable for real-time analysis where speed is essential, such as in monitoring and troubleshooting high-speed electronic high-resolution application. Since the rectangular window doesn't taper the signal, it provides the highest frequency resolution. This is valuable when observing signals with closely spaced spectral components. Lastly, transient signal analysis. The rectangular window is suitable for analyzing short bursts or transients of signal, where maintaining the full amplitude of the signal within the observation period is critical. In conclusion, the Gaussian window is ideal for applications requiring high precision, minimal spectral leakage, and smooth transitions, but it sacrifices frequency resolution. The rectangular window, while computationally simple and efficient, has higher side lobe levels and poor spectral decay suppression, making it less suitable for high accuracy tasks. The choice between them depends on the balance between accuracy and processing speed needed for the specific application.